Hello, everyone, and welcome to this episode of Science with QuEra. Today, we're going to be discussing robust quantum reservoir computing for molecular property prediction. This is a paper that appeared on arXiv 2412.06758v1. I'm very happy to have many of the co-authors here. Thomas from Merck, Milan from QuEra, Zoran from Amgen, and Dan from Deloitte. My name is Yuval Boger. I'm Chief Commercial Officer of QuEra, and very happy that everyone is here. Here is what we're going to do today. I'm going to give a quick introduction about QuEra and what we do. Then I'll ask perhaps Zoran to talk about the motivation for this study, or Thomas, you're welcome to chime in as well. Why did we get started with this? Milan from QuEra will talk about the methods, sort of the concept of quantum reservoir computing and why we're doing it and what can it achieve. Dan from Deloitte will talk about the results that we were able to achieve with this study. And then perhaps Zoran and Thomas, who are sort of representing potential end users from Amgen and Merck, can talk about the implications. For everyone on this call, there's a Q&A box at the bottom of your screen. Please feel free to submit questions at any time, and I'll do my best to weave them into the conversation. Very good. So QuEra. QuEra is headquartered in Boston, close to Harvard and MIT. We were founded by groundbreaking research from Harvard and MIT labs. We build quantum computers, but we build them because we want to help customers tackle the hardest problems and make groundbreaking discoveries. Our quantum computers, actually, we call them quantum supercomputers, are based on neutral atoms. And I'll talk in a little bit about why we believe it's the most promising quantum technology. There are other ways to build quantum computers, but we think this is the right one. In neutral atoms, we're both the scientific leader in terms of quantum error correction and other developments, as well as the commercial leader. We were fortunate to receive funding of about $230 million recently, led by Google and SoftBank, with participation from Deloitte and many of our existing investors. So we're here to stay, and we're here to solve customer problems. And what we do is we form deep partnerships with a select group of organizations. These days, given the company size and our focus on creating next generation computers, we don't work with everyone. We try to be a little bit picky in who we work with. We look for companies that are serious about quantum, and we try to do amazing stuff together. I spoke a little bit about neutral atoms. Why are they interesting? Well, neutral atoms, one is the scalability. Quantum computers will become truly useful when they have lots and lots and lots of qubits. And with neutral atoms, we can see how we can pack tens of thousands or maybe hundreds of thousands of qubits on a single machine. For us, a qubit is an atom. And only beyond that, we're going to need to start networking machines. Neutral atoms is also very efficient in terms of control. We can use very few controls to control a lot of qubits. And that's important because in other technologies, for instance, if you need 2 or 3 wires to control every qubit and you've got 10,000 qubits, and you're going to have 30,000 wires to worry about routing and noise and cooling and what have you. Speaking of cooling, neutral atoms operate at room temperature. We do not need cryogenic cooling, and therefore it's very easy to deploy in data centers. We have the technology to move atoms around and so when we want 2 qubits to interact, we can essentially bring them together close to each other. And that ability to shuttle qubits is very advantageous in terms of creating efficient algorithms, of implementing quantum error correction schemes that are not possible with static qubits. These atoms are natural. We use rubidium-87, and they're perfect. They're perfect in the sense that we can take a million atoms and they'll be perfectly identical. There are no manufacturing variations. And we operate them in a way that has high fidelity and long lifetime. And so for these and many other reasons, we believe that neutral atoms is the way to build. In November of 22, we launched our first computer on Amazon Bracket. Anyone in the world with a credit card or an Amazon Bracket account can use it this afternoon. It remains the only publicly accessible quantum computer based on neutral atoms. It has 256 qubits, one of the largest publicly accessible computers in the world, and it's available 130 hours a week. So pretty much at any time you can submit a job and you get a result fairly quickly. Lots of people have done amazing research on that, and we're here to talk about one such research. We are also continuing to move the ball forward. This is our gate-based computer, Gemini. We just finished shipping one of these to Japan, to the National Institute of Standards and Technology. It's very power efficient, it's very powerful, and it will be able to run gate-based algorithms. So we give you a choice of how to run the algorithms that you want. And last, we continue to work on next generation, third and fourth generation. This is a sort of a video that we recorded in our lab, getting as close to the optical table as the scientists would let us without revealing any top secrets. But if you're in Boston, give us a call, and if possible, we'll be happy to show you some amazing quantum computers. And last, we don't do this alone. We realized some time ago that we're really good, but we can't be the best at everything. And so we collected lots of partners that can help us do that. So we come to a customer, we come with what we call the QuEra Quantum Alliance, a group of like-minded companies. They could be experts in chemistry, they could be experts in training, they could be software or middleware providers. The latest addition to the QuEra Quantum Alliance is SAS, the large statistics company, and we're always looking for new partners. Join us for QuEra.com/partners. So with that, Zoran, perhaps I can pass it to you to talk a little bit about the motivation for this study.
Thank you, Yuval. Thank you, and congratulations to your funding from Google and SoftBank. That's a huge endorsement, so that's excellent. So motivation, well, from the applied quantum perspective, one of the problems in biopharma clinical settings that you often encounter is the problem of small data sets. And so what I mean by that is the sample set, a range of about 100 to 200 samples, sometimes 300 are patients, or could be anything, right? And so it happens in a couple of very important areas. Rare diseases, oncology as well comes with very fragmented and kind of small data sets. Personalized and more focused, more recently, precision medicine, I think. Those are all areas where those small data sets occur pretty often. And so classical machine learning typically has a problem and struggles to make good predictions. There are two reasons for that. One is that it's at the surface level, it's low accuracy. And so why it happens is because most models, especially those with more parameters, can easily figure out they're smart enough to overfit on small training data sets. They'll match it perfectly, but then when you try to predict on unseen test data set, then that accuracy drops. And of course, we use things like regularization to counter that problem, but in general, with the small sample size, that's really an issue. And the other one is the large variability of model performance. So in machine learning, it's normal practice to do 5 or 10 train test data splits, so one pair and then the other and so forth, to explore the variability and see how stable those predictions are in terms of accuracy or whatever metric one chooses to use. And so what we find out is that variability is quite significant in small data sets, and that presents a challenge, of course. Now, in this paper, what we did was demonstrated that QuEra neutral atom quantum computing platform based on quantum reservoir computing, or QRC for short, that we often call it, handles both of those challenges very successfully, showing both improved accuracy over classical methods and reduced variability, which sometimes actually could be even more important than the accuracy itself. And now, if we chose a molecular area to showcase this problem, however, I think that this could be very well applied to small data sets in clinical setting when you have phase 1, phase 2 clinical trials, for example. I think that's a huge area, actually, that I think has potential for future work. From theoretical perspective, quantum computing methods that are normally used and often used today are based on quantum variational machine learning algorithms. and they have trainability issues due to vanishing gradient. In QRC, that's not a problem because that's not the underlying algorithm and the way the predictions work. And so we see that improve more robust QRC performance as the data size decreases, which is, again, usually with classical models, the performance decreases. In our case, it actually gets to be better than classical. We also used UMAP, which is manifold unifold for manifold approximation and projection. UMAP and explored embeddings, and then they're used in two models, in regression and classification, which is also very important. Using generally what's very common is classical a quantum hybrid approach, which we often deploy today. And the last thing that I would mention, which is very interesting, that QRC is very good in handling nonlinear or highly nonlinear regimes. And that's very important. QRC overlaps with nonlinear dynamic systems with chaos theory. And so the training on the edge of the chaos is quite interesting. We know that in short to maybe some of the neural networks, we often linearize problems because it's easier to handle it, but there are many cases where nonlinearity is really dominant, and so I think we'll talk in the closing sentences about why we think that could be applied to other problems. But I think that's really that reservoir computing and embeddings really shines. So with that, I will turn this over to Thomas, who can talk a little bit more about the history of the project. Thank you.
Yeah, thanks, Zoran. And I mean, why are we sitting here? And thanks, Yuval, also for the invitation. It happened, I think, 1.5 years back or so at one of these conferences in London at a Quantum Tech. And we still had a colleague from us who now switched from Novo Nordisk to IBM. Not sure if he's in the call, but he knows who he is. We have been this pharma panel, and we were all keen on learning what QRC could do, and we have just had no clue. And then I think there was this paper from Milan coming out mentioning what could be possible, and then we just were looking for a very long time to find a problem where we have this challenge, complex correlations, not much data. And I'm playing with quantum machine learning since, I don't know, 5-6 years. So since the very first possibilities that you can have a rotational gate. And I'm not a very big fan of this gate approach, to be honest. So over the years, I got more and more convinced that gate computing is interesting for certain kind of algorithms, but definitely, I mean, we produce challenges that we might not have under control. Yeah, where you have the quantum world, and you go back to digital, just one qubit. So personally, I think this is one way one could explore, and definitely there are some algorithms, but I'm rather more into the, let's say, analog or real quantum perspective, and this is the strange that we explore, and we just don't have any clue. And I think it will be interesting to learn how the embeddings look, because always for quantum computing, it's tough to take real world data like what we did. We did in principle a table, an annotated table, and loaded it into some quantumish data, and then we have quantum happen, and then we interpret the stuff. So for me, this is one of the very brave ideas to explore this for real world problems. And then, as Zoran mentioned, for real applications, we in the healthcare industry or the pharma industry, we have a lot of small data with complex correlations. So let's just give it a try. And I think, I'm not sure who's going to take the lead, so, Milan or Daniel for the.
So maybe
It's of some slides now.
Thank you, Thomas. And Milan, maybe you could explain a little bit about the background and how quantum reservoir computing works. What's unique about it? Why are neutral atom computers a good fit for reservoir computing?
Oh yeah, certainly, and thanks to Yuval, Thomas, and Zoran for the very nice introduction. Some of it was certainly already covered by the excellent intros, but I don't think we should sort of pitch machine learning itself too much to this audience. But one thing is certainly good to keep in mind, that machine learning is unreasonably successful due to the data that we provided. So it's a database computation paradigm. And, if we believe quantum is to have a future, quantum machine learning is certainly going to be critical. So what is the prospect for quantum machine learning advantage, if you like? And one of the clearest prospects that we see is in the quantum data itself. So in this sort of matrix, as you can see, sort of we can imagine several settings in which we generate large amounts of quantum data. So already from the current quantum hardware, sort of our experiments are generating data. Our experiments are generating quantum states, which we then have to project out and probe, which is also losing some of that data. And this is certainly a place where you expect quantum machine learning to be able to sort of use quantum data better. And the second place where we expect sort of quantum machine learning to potentially provide value is in the classical data that has hidden quantum correlations. And let me make both of these just a little bit more concrete. Yeah. So the first sort of type of sort of data where quantum is really expected to have advantages is sort of this explicit quantum data. And here is an example of an experiment where in Google they try to answer certain questions about the properties of the quantum states that were prepared on their quantum computer a couple of years back. And it turns out that if you ask these questions, rather precisely, if the quantum state was prepared by time reversal, symmetric or non-symmetric evolution, you get that your classical method, given the data provided from that state, is completely incapable of answering this question, while the quantum method, which includes additional sort of quantum layers that are applied directly in the quantum computer, can answer this question perfectly. Also, at the time and sort of until recently, this was the largest successful quantum machine learning experiment to date, with 40 qubits being used. The second sort of example of potential uses of quantum machine learning is sort of a little bit more intricate, and it relates to classical data that has some hidden quantum correlations. I won't go much into detail here, so I sort of leave it as a homework to our participants. But if you analyze this paragraph of text, you can see that there are certain pronouns there, mainly this one of them one and one of them two, and the meaning of these pronouns depends critically on the context in the rest of the text. And it turns out, if you actually analyze the probability distribution of the meanings versus context, you get you violate Bell inequality with this probability distribution. So this is a surprising example in a real world text where you actually have quantum correlations hidden in the text. So it is these kinds of sort of classical data with hidden quantum correlations that we also hope could bring a potential to quantum machine learning earlier than the quantum data itself. And specifically, the question that we wanted to ask in this collaboration is there some potential in terms of materials and drug properties that sort of has these correlations that quantum is able to capture better? And then, if we believe that, and there certainly are at least these examples shown here, where quantum machine learning has advantage, what are the potential algorithms for it? And I'll go through this, fairly quickly, as a lot of it was covered by Thomas and Zoran. But the algorithms we were particularly interested in is reservoir computing. And the idea of reservoir is to use a predictive power of a dynamical physical system in order to replace huge network of nodes. And in particular, sort of an interesting property of the classical reservoir is that it can often do training in a gradient-free fashion. So you'll typically encode your data into the dynamics of a physical system, but you would not train that physical system itself. You would just train on its outputs with some very typically very simple method like a linear regression. And also, it's as Zoran has mentioned, there are several successful applications of such method, specifically in chaotic dynamics prediction and in hybrid deployment and climate modeling that show its power. However, what we wanted to do is do a quantum version of the reservoir, and specifically quantum version of the reservoir that's well suited for a neutral atom system. So this is an algorithm that we developed for our analog QuEra system, and it essentially contains three parts. The first part is classical data pre-processing, and in terms of the data set that we are talking about today, then we'll have much more to say. There is a lot of art that can go in there, but the basic idea is to put the data into the form that the quantum computer can readily process. The next step is sort of critical for the performance, and in this step we are using the programmability that is available on our analog system to encode this data in one of the three possibilities, either in the shape of the global pulses, in the positions of the atoms, or in the strength of the pulses on each atom. Whichever way we encode, the next step is the same, and it consists of performing quantum dynamics on a large array of qubits, probing the dynamics, extracting measurements, and then these measurements form essentially a new representation of data that we call embeddings. And these embeddings can then further be used in the classical post-processing step. And again, there's a lot of art there. Ben will cover some possible approaches, but the goal of the classical step is to actually train a classical neural net on top of your quantum embeddings and use that for predictions later. So immediately from the construction, you can see several important advantages of QRC. Some of it is specifically over other common quantum algorithms, such as variation of QML, mainly that since we're not training the quantum part, it works as a reservoir. It's very trainable, and it's also resource frugal since we have to query our quantum computer much less. However, some of the good properties also come from its classical limit itself. So if we introduce noise in the system, our reservoir becomes more classical, but that doesn't mean it loses performance. It just loses quantumness, which we don't like, but there is still a baseline of performance. It turns out this method, as we'll show, is very scalable, or even on current system, it can process a wide range of data, as Dan's example will show very clearly. And the biggest thing that we're excited about is that if we perform this quantum dynamics on a large number of qubits, we have a potentially classically tractable embeddings. So embeddings that you would have a very hard time of generating on a classical computer. So with that in mind, let me just, before switching to then, show some highlights of our recent experiments with reservoir computing on QuEra. In particular, this is an experiment that we did on MNIST dataset, and it sort of tests the viability of the method. And as you can see here from the last bar here, the performance of QuEra is within 0.5% of sample numerical simulation, meaning that this algorithm indeed works on hardware as expected. And one thing to keep in mind, however, when working on hardware, is that you have to draw enough samples in order to reach eventual performance limits on the hardware, and that can sometimes be hundreds of samples per data point. This was sort of an experiment on a small qubit area of about 8 or 9 qubits on MNIST. But what we really wanted to show is that the algorithm is scalable. And here is a data set in which we explore this scalability. And it's a simply classification of these tomato images according to whether they're healthy or diseased with one of the two diseases. This is the way we encode these images in our neutral atom hardware. It's simply with a 2D position encoding. And these are the results on our hardware where we show test accuracy as a function of number of qubits all the way from 9 to 108 qubits. And as you can see, QRC performance on QuEra constantly increases with the number of qubits, and it at 108 qubits is sort of comparable to the classical performance limits on this set. So with this experiment, we have essentially demonstrated the biggest successful quantum machine learning to date on 108 qubits, and we already mentioned previous record from Google on 40 qubits. However, we didn't want to stop there. We also wanted to explore potential for classical intractability that naturally comes when you consider experiments on 100 or so qubits. And in particular, we use the recent idea of kernel relabeling, where we use our sort of classical data. We don't touch its features at all, but we, however, rename the labels of the data set such that the resulting labels sort of best fit the geometry introduced by the quantum reservoir versus, let's say, classical reservoir that we're comparing to. But the basic idea is you still end up with a classical data set that now has imprinted synthetic quantum correlations in its labels. And once we do that, actually on QuEra, we see that in the example where previously QuEra was a little bit worse than classical due to the finite samples rule, we now have a clear advantage of QuEra. And furthermore, as we scale up the number of samples, we observe that the disadvantage requires much less samples than sort of the original data sets, and already about with 20 samples, we can get this sizable, as I call it, comparative quantum kernel advantage. So to conclude and get it over to Dan for a very, very exciting results on drug property data set. With Reservoir, we are able to do quantum machine learning on an unprecedented scale with a potential for quantum advantage. And if you think about where can that potential lie, so obviously this is a synthetic data set, the one that we attempted in our paper, so it's not something that you can directly imagine being useful. Well, I think the best answer to that is we need to work together and to find use cases and data where something like that could be realized. And with that, I would take it over to Daniel, and let's see one of these use cases.
Thanks, Milan. Can you stop sharing? Okay, great. So here are the results that we got in our paper. And can you see my screen? Looks like you can. But basically why we're interested in quantum reservoir computing is it solves a lot of the problems that we've had. You can do multi-class classification, you can do regression, you can do time series. It's a very handy tool, but also it solves some of the problems we have doing basically machine learning with a quantum computer. Is a lot of the earlier models were parameterized circuits. You're actually running a model that's hybrid, and you're going back and forth between a quantum machine and a classical machine to do some sort of optimization. And or it's a layer in a neural network, and the other part of the neural network is on a classical system, and there's a lot of latency, and it's just not. There's a lot of issues that come from that. So the idea of just doing all the quantum up front, you're doing an embedding of the data. You're encoding this data into a higher dimensional space. You can learn some interesting relationships using this quantum technique. It seems to be for smaller data, doing more with less data. And so, what we did was to explore this idea that quantum machine learning can be better for smaller data sets. So Maria Schuld kind of had this idea that when you have a quantum algorithm can learn more per row of data or per instance of data. And so we kind of wanted to test that. Originally, we took a data set that was very small, but then you only really know are you only using this one small data set. So what we did was we said, how about this? How about we take a bunch of samples from a larger data set and see if they're consistent, if we can get some sort of consistent advantage using quantum reservoir computing with the QuEra. So what we did was we basically took a bunch of subsamples of 100 records, 200 records, 800 records, and then we compared it to all the data. And what we found is that, when we were using the quantum reservoir computing method and we compare it to either just the raw features or some sort of classical embedding, we actually got this statistically significant difference for these 100 and 200 record samples. And here's the process we went through to get at that. The left-hand side is basically just data science fundamentals. So we took this, fairly large data set. We did some exploratory data analysis, some data cleaning, feature engineering, all that kind of things. And then created basically just a modeling pipeline where we created a bunch of test models. So on the classical side, we run about 13 different models. And we just kind of picked the best one as random forest. That's what wound up being our best model for across all the model types. And then we basically just selected the most important features and got rid of a lot of the noise out of the model. And to ensure that our samples, like when we are taking subsamples out, we're actually creating valid subsamples that represent the larger population. We actually created a clustering-based method to do the subsampling to try to ensure that, we're not just pulling a bunch of, like the first 100 records or, whatever. Like we're creating really, we are taking samples from a larger population that is still representative of that larger population of the entire data set. And then we go on to the QRC pipeline, which I think Milan's described in a lot more detail, but basically we're taking this quantum reservoir computing algorithm, we're encoding this data essentially to the physical system of the quantum reservoir computer using local detuning. We create these embeddings, we pass the embeddings into the classical models as the input, and then we're doing prediction, in this case, using random forest ensemble methods. And then we pass this into the classical modeling pipeline. And then the interesting part is we actually looked at it. Hey, what is the difference between the nonlinear effects and the linear effects? So we assume it. So we remove the nonlinear effects. We did this quantum reservoir computing one body encoding, and then we said, well, let's actually include the nonlinear effects too, see if there's a difference. And then we got our results. And we also wanted to see, is there some sort of structure to this data that could explain the difference between the classical raw features and the quantum reservoir computing embedded features and classical embedding, like, just a kernel method. We were using a Gaussian process regressor for that. And here's our top line results. So as you can see, these left two bars are the classical methods. So this is just regular old features. And these are when we embed them using Gaussian radial basis function. This is basically just a kernel method. And then we compare this to this bar on the right. So we have statistically significant, beyond the margin of error, differences in how the score has improved for these 25 subsamples. So we took 25 subsamples of 100 records, and we got a significant difference. However, we found that there was a lot of, when we don't have these when we only use the linear effects and we exclude the nonlinear effects, so that when we have the one body embedding versus the two body embedding, we found that it's kind of all over the place, that there's something really important about using the two body embedding that improves our results. And that's something we want to explore further. How does this nonlinearity affect that? And so essentially, we consistently found that for 100 and 200 record samples, there's a difference. There's improvement using the quantum reservoir embedding. However, as we increase the size of the samples, we have 800 or, all the records, we didn't find any difference anymore. And this indicates to us that we are learning more per record using QRC. And to try to get at why this might be, we applied UMAP. So we visualized the embeddings. As you can see, the classical embedding method that we used, Gaussian process regressor kernels, it's kind of all over the place. The classical raw features, you can kind of see there's a little bit of a pattern. You can kind of see here, there's this high pattern here, but it's also kind of all over the place. When we're, you can kind of see there's a pattern a little bit, but when you use the QRC embeddings, you can see there's a much clearer pattern. It's like, here's the high, here's the low, here's the high, here's the low. Whereas in the classical methods, it's not as clear. And as you get more records, it seems to be a bit of a clearer pattern. So we were trying to figure out exactly what the statistical properties are. Is something we're trying to still explore more in our future research. But so far, we've seen that there is some sort of encoding going on that is granting a clearer structure when we project it into a two-dimensional space. And that shows us that, this is creating some sort of pattern in the data that just isn't being represented classically, and that this is perhaps, open the debate a little bit, but why we feel there is a improvement using the QRC embedding method for predicting these drug discovery properties. All right, and that is my chunk.
And then, how sophisticated were the classical methods that you experimented with? Sometimes when people compare quantum to classical, they take a really simple classical algorithm and say, oh yeah, we can beat that, but not sort of state-of-the-art methods. Maybe you could comment on that.
Well, actually, we're the quantum reservoir computing it's hybrid. So basically, we're using the quantum reservoir embedding as input for the classical data. So that gets around some of these messy situations with a hybrid compute. But when hybrid being quantum and classical, but compared to the other embedding methods we use that were classical, so we use Gaussian process regressor, which is like kind of the best of the best. We actually use just a pretty simple SVM kernel too, and that didn't perform well at all. But basically, compared to the classical embedding methods, they didn't, with the data we had, with the number of records we had, we didn't really see a super clear pattern with the classical. When you look at the UMAP, when you try to project it in two-dimensional space, it's kind of all over the place. It was not really better than than just using the regular data unencoded, unembedded. So when we do the embedding with the QRC, you can kind of see like there was a really clear pattern, and there was a gradient almost. So there is some structure being implemented by this nonlinearity that is going on with QRC, the way the QRC is embedding the data, the local detuning is encoding it onto the qubits. But with the classical method, we were just finding that, even though that they were slightly better than just using the regular raw data, they weren't significantly better. Whereas QRC was doing something with lower amounts of data that was better. However, that does change when you get the higher numbers of records. When you get a lot of records, you find that the classical methods do better, just because there's more data. They're able to handle that. And I mean, it's not that they're better. It's just that the difference is not statistically significant anymore.
In Milan, maybe you could comment on how many qubits did we use in this analysis, and whether you think that Dan mentioned as the number of samples became larger and larger, then quantum and classical became very similar. Do you think quantum might overcome classical even in these large data samples if we used even more qubits?
Yeah, it's a good question. I think it's worth noting that this analysis was done, I believe, with up to 18 qubits. Then I might be a little bit rusty on the number. So this is the place where classical can still simulate our QRC embeddings, but the success that we observe, both in the interpretability in terms of UMAP and the raw performance with decreased data size, certainly leads us to ask, what could we do with more qubits at the spot where quantum can no longer simulate what we're doing. And, one can quickly reach that with at least, for example, 40 to 50 qubits.
And Thomas, I think you wanted to add something about the details of the QRC embeddings, and there was a question from the audience that
in parallel, I chatted with Milan, and because I checked out the question wrongly, but I think it's nevertheless. Let me comment on this, because I think it comes to the fundamental difference of what this analog quantum stuff can do, and also these embeddings, because that's why we did this example, this project at all. Zoran and myself, so we're standing there at the same question. So what is it about? And I think if you look at the nonlinear correlations, or what the physics behind it, so you have a kind of a atomic chain, and then you check the local distances and the influences one atom has on the next one, and on the next one, and on the next one. And because this is Rydberg, it's kind of a sixth order distance dependency. And then, of course, things can get quite complex if you encode your information on one, and then you have all these multiple interactions between each other. And this brings me to the scaling. Why do we need much more qubits? And not only in simulation, but in real. So for example, we have, maybe we'll talk about this later in a few seconds more, but as a potential use case, what I want to do is time series classification or time series prediction, which could really make sense if you have an assumption that you have physical correlations in your time series, whatever, or multiple parameters influencing this, like a, I don't know, Fourier spectrum, but in good, so Fourier analysis, but in real. And then I think all these nonlinear things happen just out of the box without needing to training it and putting assumptions in it. And this is, I think, when you can then use not only the distance of the next atom, but also in 2 dimensions, or I doubt that we will have 3 dimensions in the near term, at least in a 2D grid, you can encode very much many information. And I think this is where it's just getting interesting. And I mean, we are in these early phases where analog quantum computing is maybe having a I don't know, renaissance or not. I don't know. But I mean, it's very explorative, and let's just play with it. And therefore, I think there is no need to work with algorithmic implementations of digital data, so retransforming gates and angles with ton or whatever, but because it's just really physical. It's analog already. Does this make sense?
It does. Yeah, thank you. And Goran, maybe you could comment, what do these results tell you, and what would you like to see as perhaps future research directions?
Oh, there is so much. Right. So I think other than small data sets and predictions there, which we talked about, I think from QuEra embeddings perspective, I think it would be really interesting to see if we can use it for synthetic data generation and upsampling from small data sets. That's often a great need for that. Also imputations, which are about underlying data distributions. If you match nonlinearity there better, I think that would be a great area, because EHR data sets, electronic health records, come with lots of missing data, if you like, just the nature of the process. So those are 2 very practical areas. I think anomaly detection, outliers, also analysis that has lots of nonlinearity with it. I think that's a very important area in all of the research in clinical and medical setting. And then I think there are 2 related areas which are becoming now very interesting when it comes to AI and LLMs. I think one is that there have been a couple of research papers on this, where quantum computing is being used, their ideas and some results, to improve the attention mechanism inside the transformer model architecture, which is the key part of LLMs. So I think that's where quantum is now giving kind of help to LLMs in some way. And then I think prompt engineering is also emerging as a process that has stochastic nature in it in different ways. And I think that nonlinearity could be potentially connected with the QRC as well. I think there is quite a bit of potential there. So I think those are probably the main 4 or 5 areas that I can think of.
And I can maybe just add on these, Zoran, from coming back to what we are currently exploring is we have presented this at a conference, so I think I can talk about it. So we are looking at the voice, so the sound of the voice as a potential relevant biomarker in clinical neurologic diseases or whatever. There is evidence there are classical machine learning approaches that are validated already, so these work. And my dream would be to have an audio signal fed into a time series prediction. So I know that Milan is now shaking his head, because it's quite technically complicated. So if we think about an analog signal and we have audio and frequencies of 440 kilohertz and we have 3-second samples, so there's quite a significant amount of data. And if we look at the execution speed of the machines, maybe we stretch it by a factor of 1,000. So I think the computation would be just very long. So it would maybe take a week or so, just QPU time. But you never know. And I think this is the ideas that I really want to check in, how far we can make use of real data, real patient data, to progress this directly on the machine. And again, as you said, Zoran, we in healthcare, if we talk about these rare diseases, so there are maybe not many people who have the same disease, and just to help out doctors to identify this is now this linear graph is then not the person is drunk. So it's also for educational purpose. And I mean, to bet everything on quantum is maybe a bit overdone, but I think it's definitely one method that could help identify potentially novel algorithms also outside of quantum, so inspire things. I think it's always coming back to a dance, and I really like the idea of using quantum, just testing out what works.
Yeah, and then you have time series, for example, EKG or ECG, for example. Those are areas where you have time series, but they have quantum models. And even if quantum model is not even better than classical, as long as it's comparable, could be very well used inside the ensemble approach, where you need comparable models because it handles the data, underlying data distributions differently. So that could be very valuable model to stabilize your classical machine learning predictions as well. So there is a lot that could be done.
I do have a quick note before a question for Dan. One, this is recorded and we'll share the recording post webinar with everyone. The second thing is that Milan has mentioned publication with 108 qubits and what he described as the largest quantum machine learning experiment to date. There's a link to that paper on the QuEra website under scientific publications. Dan, what I wanted to ask you, I know you had also experience with time series data. How difficult is to prepare the pre-processing pipeline if you now have a different set of data, different topic? How difficult is it to prepare the pre-processing pipeline before you can toss it into QRC?
Well, I mean, I think it's not terribly hard. I think you're basically just doing the same data science you'd be doing for anything else. Essentially, if you're doing any kind of kernel method, or you're doing just even regular data science, all you're really doing is just plugging in a module to just say, hey, I want to use this QRC method. Especially if you're working in Julia already, it's pretty trivial. You're literally just taking your data. You're saying, okay, here's, you can do feature selection. You don't have to, but then you just pass it through QRC, and then it comes out in an embedded format. Then you can just pass it straight into the model.
And
what we have had, and this comes also maybe to the encoding topic. So you might recall that we have done something which is called SHAP. So Shapley feature reduction. So very complex correlations, 1,000 variables. You don't know how many you need, so you sort the most important ones. And I think if we have now more qubits, we don't need to do SHAP. So and I think that's also quite interesting to see, and therefore this pre-massaging would be even less than if I'm right, and you just load your data.
Yeah, we could only we were restricted to what we could actually simulate, and frankly, we were using a pretty beefy machine with 128 cores, 500 gigs of RAM, and past 22 qubits, it would run. Up to 22 qubits, it took a day to do one small run. But past that, it gets exponentially bigger. So that we are getting to the point where we can't simulate beyond a certain number of qubits. So that's where it really comes into play, where you really want to run this on hardware.
Speaking of simulators, so everyone, of course, is welcome to run this on the 256 qubit Aquila that's on Amazon Bracket. But for those who want to run it on a simulator, I think, Milan, that we have an example notebook on GitHub so people can experiment with it locally. Is that the case?
Yeah, certainly. That's a very good point. I would say, you can get into the QRC immediately from the notebook, and let me just send it to everybody in the chat. There's both Python and Julia version. There's also a notebook explaining on how to submit to our Aquila quantum computer directly.
And if you're as lazy as I am, you can use QBraid and you don't have to pip install all this stuff. So
a good point as well.
Very good. Any closing comments from any of our panelists for today?
I would just say that there are so many opportunities on this, it's almost hard to prioritize, but I think that's a good problem to have. So,
absolutely. Well, thank you all very much for spending some time with me and the audience today. And for the audience, stay tuned for future episodes of Science with QuEra. So Thomas, Zoran, Dan, and Milan, thank you very much for being here today.
Thank you for hosting.
And good luck to the winner of the Lego set. I have one. It's beautiful.
Yes, we will. The winner, one of the participants, will receive an email from me asking for their physical address so we can ship one of these Lego models, these beautiful Lego models that we created of our gate-based quantum computer. Thank you very much, guys.